Good morning or good afternoon, it's Miss Bauer, and today we're going to talk about some more transformations, starting with rotations. Now, if you rotate something, all that you're doing is turning it. And if we take a look at just a graph has 4 parts, so the first quadrant, second quadrant, third quadrant, and fourth quadrant. So whenever we rotate, we have this degree of rotation that's going to rotate it around my graph. And typically what it will do is it will turn from one quadrant to the other quadrant. So how that works is if you have 4 quadrants and a full circle is 360, well then 360 divided by 4 makes it 90. So you have these turns. So there's a 90-degree turn, that's 1 quadrant over. 180 would be 2 quadrants over, 270 would be 3 quadrants over, and 360 is back to right where you start. Now, when I labeled my quadrants, remembering this is 1, 2, 3, and 4, I go counterclockwise. And that's what throws some people off with this, is that our default is counterclockwise. As I'm rotating these shapes today, I need to make sure that I'm going counterclockwise, which is to the left. Which always reminds me of the Beyonce song. So, counterclockwise. And we have formulas for this. So if it's 90 degrees, your xy is going to change to negative yx. If it's 180 degrees, your xy becomes negative x, negative y. If it's 270 degrees, then it becomes y, negative x. And if it's 360, well, 360, you're right back where you started, which is just x, y. And remember that we call this arrow notation because of the arrows. And you'll either be given the formula or you'll be given the degree of how to rotate it. So taking a look at these 3 pictures, I want you to think for a minute, which one of these is a rotation? Only one of them is a rotation. I want you to see if you could figure out which one. Now I'm going to start in picture 3, and if I notice this, so DEF, it just slides down, so this would be a translation. So this is not a rotation, this one's out. And if I wrote it as a translation, I could also say, remember that notation, I could say translates, and if I notice it just goes 5 down, so I could say 0, negative 5, remember that's vector notation. This one right here, let's go up. If you kind of notice, this flips. This is a reflection. And if you notice what's up goes down, so this reflects over my x-axis, which remember I could write like this. Which means if I take a look at this, this is our rotation. It does turn. So notice that each point kind of pivots around. So this is our rotation. Now, translation was a capital T, reflection's a lowercase r, rotation is a capital R or uppercase R, and I always say 0 first because we're spinning around the origin, we're spinning around 0. So I'm going to say 0, comma, and then the degree that I turned. Well, if we notice back to this picture, it goes from quadrant 2, so 1, 2, 3, 4. It goes from quadrant 2 to quadrant 3. And I know that it moves in that direction because remember I have to go counterclockwise, so I'm going to the left. And it goes from E to E prime, F to F prime, D to D prime. So I go 1 quadrant over. That would be 90 degrees. And that's how I can write a rotation. Now, rotations all come down to our formula up here. And so here's the way that it works. If I look at, let's just use point E for example. E originally is at negative 4, 3. Whereas E prime is at, if I count, negative 3, negative 4. So what changed? Well, the x-coordinate became the y-coordinate, and the y-coordinate became the x-coordinate, but it was made negative. Well, go look. What does a 90-degree rotation do? It flips your x and y coordinates, and it makes the first one negative. So I flipped the x and y coordinates, and then I just made the first one negative. So instead of 3, negative 4, it was negative 3, negative 4. So we're going to follow those formulas as we go through and we look at some more rotations. So taking a look, this one says rectangle ABCD, and it shows us where our coordinates are at. And it's even given to us on the graph. It says graph the image of A prime, B prime, C prime, and D prime after a rotation of 90 degrees, which can also be written like what we just had, 0, 90 degrees with that capital R. So I'm going to go look at my formula for 90 degrees, and it goes from xy to negative y, x. And the easiest way to do this is to just write out our points and then graph them. So if A is at 1, 2, I'm going to flip those coordinates and I'm going to make the first one negative. So A prime wouldn't be at 1, 2, it should be at 2, 1. I'm going to flip them, but then make the first one negative. So negative 2, 1. B prime wouldn't be at 1, 0. I'm going to flip them, so it'd be at 0, 1. And then make the first one negative. Well, you can't really make a 0 negative, so it stays. Okay, the next one is at 5, 0. So C prime, flip those, would be at 0, 5. And remember, we can't make 0 negative. And then D prime would be at 2, 5. So it goes from 5, 2 to 2, 5. But I'm going to make the first one negative, so it'd be negative 2, 5. Now, let's just pretend that we had a negative number. Let's just pretend we had point E. And E was, let's say, negative 5, negative 7. Well, according to this, I would flip them. So it would become, E prime would be negative 7, negative 5. But I need to change the symbol. The first one should be negative. 2 negatives would make that a positive. I could just erase it. So think, flip your X and Y and then make the first number the opposite of what it was. If it was negative, make it positive. Or in our case, it was positive, so we made it negative. And now I'm going to go graph these points. So A prime's at negative 2, 1, which is left 2 up 1. B prime's at 0, 1. C prime's at 0, 5. So those don't go left or right at all. They just go straight up and down. And then D prime is at negative 2, 5. So asking yourself, if it's 90 degrees, it should have gone to the left 1 quadrant over, which I can check and see it did. It turned 1 quadrant over. So instead of on the x-axis, when it spun around, now it's attached to the y-axis. And that's it. So let's take a look at another rotation. It says, find the coordinates of the image triangle PQR under this transformation 180 degrees. So let's go look at our formula for 180 degrees. Our formula is negative x, negative y. So that's nice. All I'm going to do if it's negative x, negative y is I'm just going to change the positives to negatives and change the negatives to positives. I don't need to flip the coordinates or anything like that. So first I just need to figure out where they're at. So if I look at this graph, it says this is 4 and this is 8, which means that my graph goes by 2s. So I need to be really careful here. So P, if it's, so that's 2, that's 4, P's in between, which makes that at 3. If that's 2, that's 4, it's in between. So P's at 3, 3, because notice it's in between, it's like perfectly in the middle there. Okay, Q, so remember each tick's worth 2, so the in-betweens are 1. So if this is 4 and that's 6, Q would be at 5, 4. And then R would be at 3. It's right above P, but it goes 3. So it's in between 8. And remember that's 6, that'd be 7. So R is at 3, 7. So if this were 180 degrees, I'm just going to make them negative. So P prime should be at negative 3, negative 3. Q prime should be at negative 5, negative 4. And R prime should be at negative 3, negative 7. And now I'm going to go plot those points. So P prime should be at negative 3, so that's 2, negative 4. There's negative 3 right there in between. Q prime is at negative 5, right there, negative 4. And then our last coordinate, R prime, is at negative 3, negative 7 right there. Notice that it's still congruent. Remember, that's called rigid motion. It's still congruent. It's still the same triangle. It's just turned around. And notice 180 means that it goes 2 quadrants over, so just like that. So going back, it really all revolves around these formulas. So 180 degrees will become negative x, negative y. With 90 and 270, what you'll end up doing is flipping your x and y values, whereas 90 degrees makes the first one negative and 270 makes the second one negative, so it changes that symbol. So be sure to keep these formulas close while you're working on your practice. But before that, let's take a look at dilations. A dilation is when an image gets larger or smaller, but we don't say larger or smaller, we say reduction or enlargement. So dilations are our only non-rigid transformation. And if you think back to non-rigid means that the size changes. These are not congruent. It might be the same shape, but it's definitely not the same size anymore. So it says for the given dilations, find your scale factor and determine if it's an enlargement or reduction. Now remember, our scale factor formula is new over old. Think of it like pancakes or clothes. New, whenever you're making pancakes, you put the fresh pancake, the new one, on top of the old one. And clothes, typically if you go shopping, doesn't your new stuff go at the front of your closet? It's the same thing with our scale factor formula, new over old. So I need to be careful though and figure out which one is the old and which one is the new. And it all boils down to those primes. So remember that we call that one our image, which would make the one without the primes our pre-image or our before. So the way that this works is I'm just going to pick a point. It doesn't matter which point I pick. I'm just going to go with M and M because it's right there. I'm going to figure out where each one is at. So M is at 4, 4. And M prime is at 2, 2. Well, without finding the scale factor, you can probably figure out, is it an enlargement or is it a reduction? And this is going to be a reduction because it gets smaller. And now I'm going to figure out my scale factor. So scale factor is just new over old. I'm going to pick one coordinate. I'm going to go with the y. It happens to be the same for both. So I'm going to put one part over one part. So I'm going to do 4 over 2. Well, 4 over 2. Oh, my bad. Sorry, y'all. Ignore that. Okay, so new over old. So it would be 2 over 4 because I do the prime over the old one. And so 2 over 4, which would reduce to 1/2 or 0.5. So there's your scale factor. Now, let's just say that we had to write it in proper notation. Well, dilations are written with a capital D, 0 at the beginning. So rotations and dilations have this in common. We always say 0 because we always talk about we're turning around the center or we're using the center of the graph. Comma, my scale factor was 0.5, or you could say 1/2. Now, that's one way to write it. The other way to write it is to say arrow notation. I could say x comma y arrow, and I could say 1/2 x comma 1/2 y. Either one of these work for a dilation. Either one of these is a way to write a dilation. And we knew that it was a reduction because it shrunk. It was a reduction. It goes in, it gets smaller. Okay, so let's take a look at another one. So I have PQRS right there, and then PSRQ right there. If I look at it, I can still tell that the black one is my pre-image. There's no primes. And then the one with the primes is the image. Okay, I'm going to pick a point, and it doesn't matter which point you pick. I'm going to go with S again. So if I count, S is 8, 4. And then S is at 4, 2. Now, the X and the Y coordinates are different. Before it was 4, 4, 2, 2. That was nice. It doesn't really matter. And without even checking, like scale reduction, your scale factor is less than 1. You can kind of look at this and tell it gets bigger. From here to here, it gets bigger. So this is an enlargement. Our scale factor should be greater than 1. So most students tend to like dilations because you can kind of use your eyes and see. Most of our graphs are to scale. So you can use your eyes and look at it and see, is it getting bigger? Is it getting smaller? And go from there. So to find the scale factor, I just need to pick one part of this. I'm going to use the X coordinate. Oh, it doesn't matter which one. And I'm going to do new over old. So be careful. Would it be 4 over 8 or 8 over 4 if I'm doing new over old? And if you said 8 over 4, you're right. 8 over 4 would be 2. There's our scale factor. And notice it's greater than 1, and enlargement, we were right. Now, if we were going to use that annotating from above, so copying that same pattern, I could write a dilation. I could say capital D, 0 as my center of the dilation, and then my scale factor was 2. So I'm going to say 0, 2. I could also just say xy, arrow, 2x, 2y. Because isn't that what we did? Didn't we just double the x and double the y? Isn't that what our scale factor is? And that's dilations. So let's take a look at a few more. It says find the coordinate under the given transformation. Okay, capital D means it's a dilation. They told you the scale factor right here is 2. So all you're going to do is multiply each number by 2. So 1 times 2 would be 2. -5 times 2 would be -10. And that's what we're going to do in just a second when we graph these, is you're just going to multiply all the ordered pairs and you're good to go. Okay, this one we have 0.5 as our scale factor. So 0.5 would shrink this. That would be a reduction, and my point's 0.6. So if you ask yourself, what's half of 0? Well, half of 0 would just be 0. And then if you ask yourself, what's half of 6? Half of 6 would just be 3, and that's it. And then for our next one, it has a really big scale factor of 10. That would be an enlargement. That would be 10 times the size. But if you have the point 0, 0, well, what's 0, 0 times 10? It's still just 0, 0. And that's typically because we use the center of our dilation as our center, and so that center wouldn't be changing. So if you have 0, 0 and you dilate it, you shrink it, enlarge it, reduction, it would still be 0, 0. So taking a look, it says if the vertices of triangle ABC are A's at 1, 2, B's at -2, 1, and C's at -1, -1, use an algebraic representation to find the coordinates of triangle A prime, B prime, C prime, the image, so the new one of triangle ABC, using this rule. Okay, well, the capital D tells me that it's a dilation. 0 is the center, and my scale factor is 3, because that's the second number. 0 will always be the center. So I know that it's a dilation with a scale factor of 3. Here's going to be my algebraic representation. I'm just going to say xy, arrow. Well, then I'm going to multiply each number by 3. So I'm going to say 3x, 3y. And that's it. That's your algebraic representation. I'm just stating what I'm going to do. This notation didn't tell me what I was going to really do. It gives me the scale factor, but this is my algebraic representation. So if I were going to find A prime, B prime, and C prime, all that I'm going to do is just take these numbers and multiply them by 3, every single one. So if I have 1, 2, we'll multiply by 3. A prime would be at 3, 6. If I have -2, 1, multiply it by 3, that would be at -6, 3. If I have -1, -1, multiply each piece by 3, that would be -3, -3, and that's it. That's how you find your points. So here we go. It says, what are the coordinates of the vertices? And I have this dilation, because I have capital D, and it tells me the scale factor is 2 of this triangle. And then it says, graph the image of this triangle. So I'm just going to figure out where are my original points, and then I'm just going to multiply them by 2. So I see that P's at 2, -1. I see that Z is at -2, 1. So we're running before we rise. I know that tends to throw some people off, but remember that we're doing X first before Y. So we're going to run before we rise. So I'm going left or right and then over. So this one doesn't run at all. Point G doesn't run at all. So that would be 0, so 0, and then it goes down 2. So that would be 0, -2. I know that tends to throw some students off that we're doing X and then Y. So if my scale factor is 2, to find P prime, I'm just going to double it. So then it would become 4, -2. So I'm going to go over to my graph, and remember I'm running. So I'm going to go right 4, down 2, and that would be point P prime. That's it. Z's at -2, 1. So Z prime, if I double each of those numbers, that would be -4, 2. I'm just multiplying each one by 2. And most of your scale factors will be pretty small. It's kind of nice. You can do some mental math there. So if that's 4, -2, that means that I'm going to go left 4 and then up 2. And remember, my scale factor was 2. This should be an enlargement, so notice that it's stretching. Okay, and then if g's at 0, -2, well, g prime should be at 0, because 2 times 0 is 0. To -2 times 4 would make that -4. So there's g prime. So g prime would be at 0, -4. It's going to go off the graph, and that's okay. You're going to go off your graph sometimes. Sometimes we just have a scale factor or something, and the graph didn't quite fit. It's all good. Connect them. And that's my image. I have a new triangle that's double the size of the old one. And notice that this point didn't really change. Like, it's still on the triangle. It's the rest of the triangle that ended up being stretched because we use this as our center. And that's it. That's dilations. So we've gone over translations, reflections, rotations. Hopefully you're feeling good. Don't forget that a translation is just a slide, a reflection's a flip, a rotation's a turn, and a dilation gets bigger or smaller. And then we're going to take a look at symmetry in shapes. So symmetry isn't quite a transformation in the sense that it's on a graph and we transform it, but symmetry is just looking at a shape and asking yourself, is it symmetrical? And so reflectional symmetry is whenever your shape can fold. And rotational symmetry is whenever your shape can turn and be the same. So every time that we had a reflection, my graph as a whole could be folded along the line of symmetry. Every time I have a rotation, I can turn it and end up with that same picture again, because that's what a rotation is. So just going over a few of these, is an arrow would have a line of symmetry, because I could fold it right there and end up with the exact same thing. So I could say that this arrow has reflectional symmetry. Now, it only has rotational symmetry if I can turn it and end up with the same thing. I would have to turn this all the way around to end up with the same thing. But if I take a look at this sun, well, every time I turn the sun, I would still end up with the same exact looking sun. So this would be an example of a shape that has rotational symmetry and reflectional symmetry. And not all shapes have symmetry. If we take a look at this shape right here, ask yourself, is there any way that we could fold it? Or is there any way that we could turn it for it to be symmetrical? And the answer is no. Unfortunately, there's no symmetry. So that's just something to keep in the back of your head. You can cross out those other examples. I just want you to remember that there's two types of symmetry. And if we look at some of our transformations, I notice that reflection has reflectional symmetry. A rotation turns and has rotational symmetry. Keeping in mind that all of these were congruent in rigid motion with the exception of dilations. That's it for today. Good luck on your practice.